Hello. 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 Is it working? Is it working? Sorry? Guys at the end, am I audible? Audible? Cool. Shall we begin then? Okay, so before we go, can I just get a show of hands of people, as in how many of you already have a prior experience in, say, quantum mechanics or quantum computation? Bit of experience, a bit of... Cool. So this session is going to be introductory in this sense that given the prior information, the prior source of information these days being Instagram, there's a lot of misconception around this quantum word, and like you can go ahead and add quantum before anything. There's quantum optics, there's quantum electrodynamics, there's quantum mechanics, there's quantum everything. So there's a lot of misconceptions surrounding it. So I'd like to take this opportunity to maybe clear some of them out, maybe establish some fundamentals so that the next weeks when you actually go and code in your laptop, you know what is actually happening in your laptop, and at the same time explore a bit like what's happening in the current research arenas and talk a little bit about my work, what I do. So the title being Beyond Qubits. So we just celebrated the 100 years of quantum mechanics back in 1925. So it starts from 1900 when Max Planck for the first time introduced the concept of quanta. So he was able to explain how black body radiation occurs using this concept of quanta. Fast forward to 1925, Schrödinger was able to come out with this very famous Schrödinger's equation, which I guess a lot of you know about. Even if you don't understand the physics about it, you must have seen it somewhere. So back in 1925, Schrödinger came up with the Schrödinger's equation. That was a way to explain how quantum systems in general work. But then it was not easy. Like for the next 30 years, the physicists were scratching their head trying to understand how things are actually working. Like the biggest minds, say Albert Einstein, he was not able to appreciate what was happening, and he didn't want to accept he didn't want to accept what quantum mechanics were actually predicting. So the very famous quote being, "God doesn't play with dice." Again, it's something that a lot of you must have heard. So following the 30 years after 1925, there has been a lot of duels. The forefathers of quantum mechanics being Schrödinger, Einstein, Niels Bohr, Heisenberg, de Broglie. But as we pass the century, today we are standing at a point where this is not just a theoretical battleground anymore. Today, the biggest of companies, say Google, IBM, and even new quantum-based companies like D-Wave and many more, they are pouring billions and billions of dollars for this so-called quantum thing. So what has suddenly happened? What has changed that from being a theoretical battleground, this has turned into an industrial war zone? So maybe I'd like to take you through that. So for that, let's first see how we reached where we are today. So this is a very concise history of how everything happened. So again, 1925, the Schrödinger's equation came into the picture. The idea of quantum mechanics was thrown out to the world. For the next 30 years, there have been a lot of debates. There have been this very famous, there have been many explanations of what quantum mechanics is. For example, the Copenhagen interpretation, the many world interpretations, and so on and so forth. For the next 30-40 years, quantum mechanics developed its foundations, but quantum mechanics was not the only field that was growing. Parallelly, classical information was also growing to the point that we were able to probe atomic structures better and better. By that, what I mean is we developed better experimental techniques. Okay, we were able to discover transistors. So we were actually ending up to a point where we can actually process classical information at a better stage. Like classical information processing has been there for a long time, starting from 1800s and so. But we reached a point where we had great control over classical information and classical information processing. So what happened is, in the year 1981, for the first time, both of these fields, the classical information processing and quantum mechanics, met its coinciding point. And that is where the birth of quantum information came in, by the suggestion of great Dr. Richard Feynman. So how he proposed the idea of quantum information is following. You see, information is physical. What I mean by that is, I am passing some information to you, but I'm passing it to you through sound waves, right? Similarly, if I'm passing some digital information, it's not just information, it's some physical thing. It has to be some voltage, it has to be something physical, something that is tangible, that is something what we can see, that is something what we can measure, right? But following 1920s, people were able to establish that nature in general was quantum mechanical, right? People could understand that the classical laws are not the complete laws. There's something way beyond that. And as we developed, we end up having better engineering techniques. We kept on making transistors, we kept on making instruments smaller and smaller. So what happened at the end, we reached a point where we wanted to do information processing, but quantum mechanics started to take over. So the physical information being physical, and quantum mechanics being the fundamental governing law of nature, we met a point where information processing had to incorporate quantum mechanics in it. So that was the point where Richard Feynman proposed that if we want to do information processing, and if information is physical, and if the physical nature follows quantum mechanics, then why can't we create a computer that basically follows the law of quantum mechanics? That's the very fundamental idea. And then following his revolutionary suggestion, 1994 was the first time when we actually came up with something that showed that yes, quantum information processing can be done. Shor's algorithm is something that you saw a few slides back in the quantum key distribution thing. Okay, we can't talk more about it, but I'm pretty sure in the tutorial session you'll see what these algorithms are. But the point is, in 1994, for the first time, a quantum algorithm was introduced to the world, which actually proved to be faster than a general classical algorithm. And that is a point where this quantum supremacy thing came into being, that there can be a branch of computers that can perform some tasks way better than classical computers. So we had the Shor's algorithm, a landmark in this quantum information processing, then Grover's algorithm in 96, and then fast forward to 2000s. In these 30 to 40 years, there have been a lot of theoretical work. There have been a lot of algorithms. There have been a lot of simulations that have been done to show the supremacy that can exist. But then again, the wave kind of faded because we didn't have that experimental expertise. But as the new millennia hit, as we entered 2000s, it was for the first time that we were able to establish all those theoretical things experimentally. All right, that is exactly what happened in the year 2001. Like after almost 20 years of Shor's algorithm, we were actually able to establish it experimentally, and then the world was never same again. The experimental, we entered a zone where we had greater experimental expertise, and we were able to establish one algorithms after another. And today we are at the NISQ era, which is the point where classical information has not completely taken over. It's still noise induced, but then again we can actually find some advantage in it. So we'll talk more about it. But before that, it's a time that we understand a bit of maths, like what are these qubits, what they actually are. Idea being very simple, we know that classical information is done by something what we call the classical bits. So it's either a 0 or a 1, right? Qubits are the quantum analog of those bits. Alright, they are just the quantum analogs of the bit, analog of the bits. So it's basically quantum bit, so a qubit. And now instead of a 0 and 1, we represent it with a ket 0 and a ket 1. What these kets are, I mean, it's a bit of maths involved in it, but for people who have had some experience in linear algebra, they are basically two-dimensional objects. For example, this can be an example of a set of qubit. Okay, but just for sense, just for people to understand this, these are just the analogs of the bits 0 and bits 1. Okay, but again, just creating an analog is not enough. Where is the advantage coming in? The advantage comes in this point. Earlier, for classical information, we either had something or we didn't have something, right? Either there was 5 volts or there was no volts. Either the thing was at this place or it was not in that place. But quantum mechanics is a completely different ballgame. Now we introduce a concept of superposition. The very famous Schrödinger's cat, right? You don't know the cat is alive or dead unless you open the box. Okay, I mean, I can give you a better analogy than that. Think of a spinning coin, right? Think I have a coin in my hand. Okay, it has a head or a tail, right? Like say for example, I spin the coin and throw it towards you. Alright. As I throw it towards you, the moment you catch it, you get a head or a tail, right? But the moment it's going from me to you, do you know what the state of the coin is? You don't, right? You don't. You just know that it exists in an equal superposition of 0 and 1, but you don't know what it exactly is unless you catch it and then you see it. And that is the exact idea of this quantum information processing. You can actually transport a lot of information, okay, a lot of information using this qubits because they exist in this so-called superposition state, an equal superposition of say 0 and 1. Okay, so that's the idea of superposition. But again, there are a lot of misconceptions surrounding it. People think that okay, that just means you have infinite data transferring capacity. It's not that. Again, remember, as soon as you catch it, you are actually collapsing to one of the states. That is how quantum mechanics work. Even though you are using these superposition states, as soon as you measure it, it becomes a bit. Okay, we'll not go into that much of jargon, but I guess the analogy gives you an idea how things work. So yeah, qubits are basically, in layman's term, a spinning coin for you. So you just throw a spinning coin, so that's a qubit being thrown to you. The moment you catch it, you get an information, and that's how quantum information processing is in principle done. So how are they different? Now this is a very important slide. And I like to take few minutes of my time to explain what these things are. So this is very easy to understand. It's either a 0 state or a 1 state. Cool. For quantum state, it's a superposition of 0 and 1. Fine. Representation, for classical bit, you can have representation in the form of say voltage. Like for example, if there's 5 voltage, that means it's a 1 state. If there's 0 voltage, it means a 0 state. So that's a representation of 0 and 1. For quantum states, it can be photon polarization and stuff. We'll come back to this, how they're encoded. That's a point to be discussed later. This is a very important thing, information. Classical bits are deterministic in nature and quantum bits are probabilistic in nature. Why do I say so? Quantum bits are probabilistic in nature for the reason that when I'm passing the information to you, you cannot tell what is being passed to you. Like for example, if I'm sending you a 5 volt information, you know I'm sending you 1. If I'm sending you 0, then you know I'm sending you 0. But for example, if I'm sending you a photon, you can't say if it is in upstate or downstate unless you measure it. So in that sense, it's probabilistic, right? And classical bit is deterministic. I think this is quite understandable, right? But then I have a question for you. If that's the only advantage that quantum mechanics bring in, what if I just write down a Python code, okay, with a random number generator that 50% of times generates 0 and 50% of times generate 1, and then claim that I've built a quantum computer? I mean, isn't that what I've been claiming all along? Do I make sense? I can just write down a code that 50% times predict 0, 50% times predict 1, or for that matter of fact, any arbitrary 0 and 1 condition, given that the probability is 1. Have I created a quantum computer then?
I can just copy the seed now.
Sorry?
I can copy your seed, then I can clone your seed.
Yeah.
There's a seed to it now. It's not completely it's pseudo-random.
Right?
So that's not what my thinking is. It's completely random.
Yeah, okay, but again, like I can create a state. No, like what if? So, for example, I have a state like this. This is something of a superposition state, right? This is a superposition state. I create a state that 50% of times creates 0, 50% of times create 1. Okay. You measure it. It will give you 0 50% of times, and it will give you 1 50% of times. So why do we need all this quantum jargon? You already have it in our arsenal. You can just bring out your laptop and code it in just 1 minute. So that is where quantum mechanics come. That is where quantum mechanics get even more spookier, and that is something that made Einstein go nuts about it. So what happened is, there's something called quantum entanglement. So what happened is in 1930, 35 or something, Einstein, Rosen and Podolsky, the very famous EPR paper, what Einstein did is, following the claims of quantum mechanics, he showed something, what we call the idea of quantum entanglement. What I mean by that is, suppose there are two particles that are entangled. Okay. Then if I know the information of one particle, the second one is instantaneously known. Okay. So Einstein came up with this paper, and he described this phenomena, and then claimed this to be a spooky action in distance, and saying that this is utter nonsense. This cannot exist, right? Like, his own theory has actually proved that information cannot travel faster than light. But I have something in my hand, and another thing is, say, millions of light years away. You just measure this, instantaneously you know what the other one is. So Einstein showed this and tried to prove that quantum mechanics is utter nonsense, but he actually ended up giving the biggest gift to humankind. Entanglement is something that makes the quantum jargon, so different from classical thing. Whatever you do, you can never ever simulate this correlation, that if I know something, instantaneously I know the other thing. This thing you can never ever simulate using a quantum computer. So even if you are able to do some probabilistic thing, you can never create the so-called correlation thing that exists. Okay, so there's this very famous Bell's inequality and CHSH inequality. So these are something. So the Bell's CHSH inequality is basically an identity that in classical realm is always held, but in quantum realm it's broken, indicating that there's some kind of correlation. There's some kind of connection between a pair which is not classically understood. So that is where this quantum thing is different, and that is exactly what people take advantage of. Whatever it is if it is QKD, or if it is doing quantum computation or designing the best of quantum algorithms, you will need entangled pairs for that, because that is what makes quantum computers different from classical computers. So I hope this is a misconception that is cleared out. Anyhow, so how do we operate on quantum bits, qubits? So just like in classical case, we used to have this Boolean algebra like AND or NOT stuff. For quantum case, these are some quantum gates, or what we call the unitary matrices. So as you can see, these are 2 cross 1 matrices. The corresponding operators would be some 2 cross 2 matrix. Okay, so as you can see, this 2 cross 2 matrix, when operate on this 2 cross 1 matrix, you'll get another 2 cross 1 matrix. So this is how a quantum operation is represented. I'll show you a bit more about it in the next slide. Then there's this copying thing that this gentleman was talking about. Basically, classical information can be copied, right? Like, there's an electric wire going, you just connect it and take it to your home. You're just copying classical information. Or I'm speaking right now, you can just take it out. It's not a big deal. I'm just sending you sending your WhatsApp information. Given that it's not encrypted, you can just make a copy of it and send it somewhere else. But quantum bit cannot be done so. Quantum bit cannot be copied. This very famous so-called no cloning theorem. You cannot just clone the information. It's not like that. A quantum information is going, you can just copy this out and take it out here. It's not possible. So this is a great achievement in this sense. This is one of the laying bedstone of quantum encryption. being that classical information can be copied, right? But quantum information cannot. So that gives you better encryption systems, the QKD systems that were being talked about, quantum key distribution things. And finally, parallelism. It's very similar to the deterministic and probabilistic idea. So classical bits are one at a time, of course, and quantum bits can exist in superposition. So quantum bits exist in superposition, but again, I mean, keep these things in mind. Quantum bits do exist in superposition, but quantum bits in themselves are not readable objects. You cannot just see a quantum bit flying, catch it and say, oh, this is ket 0, ket 1. You take it, you measure it. Just the moment you measure it, you get to one of the bits. It will be a 0 or a 1. But the thing is, you can send in more information by that qubit. So it's somewhat like it's a bus. Like earlier you had a bike where you could just carry one person. Now you can carry 2 person at a time. But as soon as you measure it, there's only one there. So sorry for this very poor analogy, but that's how quantum mechanics is. That's how weird this subject is. Not my fault. Anyhow, this is an example of quantum circuits. I'm pretty sure for the next weeks or so you'll be like doing bunch of these circuits and like you'll be scratching your head around it. And these words might seem very new to you, but after the 7 days, these words will be like just another set of words. So yeah, so again, this is a qubit. These are 1 qubit gates. Okay, you see this is 1 qubit gate. This is something what we call the X gate or the Pauli X gate. And that's represented by a corresponding matrix, as I just claimed. Okay. Similarly, there's another 1 qubit gate. This is called the Hadamard gate. This gate basically creates a superposition of states. This is a 2 qubit gate. So basically, the action of this will depend on the action of this. So in this case, it's a 4 cross 4 matrix, right? And then there's the C0 gate. This is also a 2 qubit gate. So you realize this. When it's acting on just 1 qubit, it's acting on a 2 cross 1 matrix. So it's a 2 cross 2 operator. But when it's acting on 2 qubits simultaneously, it's basically acting on a 4 cross 1 matrix. So then you have a 4 cross 4 operator. Again, for people with some background in linear algebra, you know that there can be vector spaces of d dimension, right? So when we are taking 2, 3 or even larger number of qubits, then you are not basically spanning it using the initial 2 cross 1 matrix. Now you need higher dimension vectors. So that's how the operators also grow in size. You'll see a lot of these in the tutorials for sure. Alright. Finally, this question, why are qubits powerful? So superposition allows parallelism in computation. Entanglement is something that classical computer can never ever recreate. And the foundation quantum algorithms such as the Shor's algorithm and Grover's algorithm are basically the main crux of how quantum computation has been set up over the years. I'd like to take a minute or so to talk a bit about, then is this the supreme computer? Like if we have a quantum computer, then it's done. Or is it like if I have a quantum computer, then I can end up solving everything? Is it so? So again, a minute of misconception clarity. It's not that all problems are in this sense useful for quantum computer, right? Like for example, we talked about the so-called protein folding problem or the quantum key distribution problem. So protein folding problem or anything of that sort comes from a classes of optimization problems. Being that, for example, think of a traveling salesman problem, a very simple problem. So for example, you have 3 cities to travel. You have 3 cities to travel, and suppose there's a salesman who has to travel all these 3 cities. So what would be the best route so that you can cover all these 3 cities? It's very easy to see, right? You can just draw it on your own. But when the number of cities basically grow, it gets to a point that it's almost intractable using classical algorithms. So the thing is, there are certain class of problems that are not easy to solve. These are called the NP problems. These so-called NP problems. Okay. And there are certain class of problems that are pretty easy to solve. What is called the P problems. Okay. For example, if I tell you there's one number say 536 and there's another number say 234. Are they factors of say some 1,36,322. It's very easy for you to check. You just multiply them and say either it is or it is not, right? So if I give you two numbers and ask you if they are factors of a certain number, you can just multiply it and give me the answer. But what if I give you that 1,36,200 and whatever the number was, and ask you to find the factors of it? It's very difficult, right? The first thing that would come to your mind is perhaps run over a loop over and over and over and over and keep checking, and it's a very difficult optimization problem. And when the number is very large, you can practically not do it. For example, for QKD systems, there was a mention of RSA encryption system, right? So this RSA encryption system does the exact thing. So it asks you to take find the factors of a very large number. In principle, that's doable, but it will just cost you the time of the entire universe's age. So if you are able to do for that long, kudos, you have cracked a WhatsApp message. But that's not what you want to do, right? So these are the so-called NP problems that are very hard to solve, and there's something called P problems. Now, where this P lies inside NP is a difficult problem. If you can answer it, then you can win $7 million, $1 million. It's one of those millennia problems, is NP is equals to P. So, this quantum algorithms come in and it creates a different class of complexity. This is called something called the BQP. This is a different set of problems. Again, we exactly don't know where this like how much of NP region does this BQP cover also, but we know for sure that all the P problems can be done in these quantum algorithms, and there are some NP problems. For example, the so-called protein folding problem or the factorization problem, even they can be done, which lie in NP but can be done using quantum computers or quantum algorithms. So this is the idea of what quantum computers can do. Yeah.
Why is P inside NP?
Yeah, because if you think it in this way, all the set of difficult problems has a smaller subset which are easily solvable. So like for example, prime factorization being a difficult problem, but checking the prime factors is easy. So it's just a subset of those difficult problems. Am I making sense? I mean, the harder problems are just a large class of problems, but then there's a part of it which is always solvable using some efficient algorithm. So that is where the P thing comes in. Does that make sense to you? Little, okay. And again, quantum computers can solve a larger area, like it can solve this P and then a larger area which encompasses few more problems of NP. And again, there is even larger class, something called NP complete and so on and so forth. For example, playing chess, that's a problem that is like even quantum computers can't do it. But apparently Elon Musk thinks it's very easy to do, so yeah. Anyway, you guys don't follow Twitter or what? Sorry, X. Okay, my bad. Anyhow, that's a basic idea of what quantum computers are and what they do. And I think it is suffice to say that we don't want a world where there's only quantum computers doing our job. We want an arena where there's classical computers and quantum computers working together to make things work, because when both of them working together can actually produce, when both of them are working together, they can produce results far greater than what quantum computers can do. So it's not we are creating an alternative version of computation or something. We are just, creating an additional component to it. So I think that is clear. This is a time complexity comparison. For example, so time complexity basically means how will your time taken for the computation grow with the size of system. So for example, the salesman problem, for 3 it's just an easy problem, but for say 10,000 or something, it's a very difficult problem. So for example, I'll look into this Shor's algorithm thing. So Shor's algorithm. So Shor's algorithm in general is a very difficult problem to solve, the integer factorization problem. its time complexity is exponential to the power of something. So what that basically means is, with the increase in system size, the time taken to solve the problem grows exponentially. All right. But for Shor's algorithm, that is just log of n. That's incredible reduce in complexity. Like, such an quantum speedup is just unbelievable. If you go back to one of those slides in quantum supremacy, like in the very first slide, I showed you something where quantum Sycamore, you must have heard about quantum Sycamore processor. These are some of the processors that have established quantum supremacy to a great extent. They have shown certain tasks can be done in like few months that will take, say, billions of years for classical computers to perform. So these are some of the time complexity stuff. You can see that there's a decent, like these two are the very important ones, the Grover's algorithm and the Shor's algorithm, the two very famous ones. So you can see it's from linear, it comes down to a square root n. Again, linear is not a very bad time complexity, but again, square root n is like, it's never bad to like have a better complexity. And of course, exponential to log n, that's a remarkable speed up. Peter Shor is a legend for that. You can search him up in YouTube. There's a lot of interesting things about him. Okay, how are qubits encoded? So for the classical bits, you remember that we did with some voltage stuff. So it's either a 1 or a 0, and or it's basically it's there or it's not there. How qubits are encoded is basically, for example, if you have some prior experience in, say, quantum mechanics, you know there's something called the harmonic oscillator, and then there are different states of it. This is the ground state, and there's this first excited state, and there are more. But if you are using some impurity able to like make this energy gap very large so that they can't propagate from one state to another, then in principle you have achieved a qubit. Like, you are just working between these two energy states. So that's exactly how ion trap qubits work. So you basically trap an ion, and then basically by careful engineering you increase the energy level to such an extent that in principle you just have two levels to work with. There are these photons. You know polarization of photons, right? There's this horizontal polarization and vertical polarization. Again, they can be used as the qubits, because like there can be one state, say the horizontal, and there can be this another state, say vertical. So these are the two different qubits. The superconducting qubits. Again, for superconducting qubits, you need some very magnificent engineering task. So what happens is there's something called transmon qubits. It works in some scale of micrometer range. Like there's a capacitor, and then there's a circuit that basically is made of the size of it's of the order of micrometer range, and there you produce this so-called transmon qubits, this superconducting qubits. This is exactly what the most top companies use these days. And then there's these NB centers. This is a very, very nascent research topic. A lot of people work on this. So again, this should make sense to you, because these experimental techniques are very recent, like falling 2000, 2010s, and so we could actually probe into these things. Before that, it was very difficult for us to even realize how they work. So now, given that we are able to probe it, we can actually use it to do the so-called quantum information processing and stuff. So that's how qubits are encoded. So that's a very fundamental idea about what this quantum information and things are. Before I move on to this next segment, I'd like to stop a bit and ask if someone would want to like know something more about this, or is there a question? What we have discussed so far. Then we'll move on to this next segment, which is not simple anymore. Like we are like, yeah.
How do you differentiate the parallelism that we achieve and the parallelism that we are going to achieve with quantum?
Sorry.
How do you differentiate
the
parallelism that we achieve with GPU program and with parallelism that we are going to achieve with quantum?
Oh, okay. So there are a lot of theoretical papers that have done this. So for example, this Shor's algorithm that has actually made this 1000 qubits and 1000 qubits thing, and they have actually calculated the time complexity and show that it can actually break the RSA thing. What with the present quantum, with the present classical computers, we can't do that. Like, of course, there has been a lot of papers that have explored how much time it takes to calculate those things. But theoretical, we already have a data, because again, it's just pure maths to do. What we are yet to do is do them experimentally. So theoretically, we can actually calculate how or what much or what time it would take for a quantum computer to perform. Is that what you were asking?
No, I mean, how do you differentiate fundamentally the parallelism with, let's say, 1,000 bits input to solve a problem, and the quantum algorithm solving it? That's what I mean.
Parallelism, as in like, how do you?
What I mean, you are saying that we achieve parallelism with quantum computing.
Yes.
Still, we are doing a lot of things parallelism using the lot of, let's say, GPU programming.
No, I don't think they're the same parallelism you're talking about. Like.
That's what I'm saying. How do you differentiate that parallelism?
Okay. So this is This is some kind of fundamental parallelism in the information itself. Okay, so qubits are parallel. Qubits have parallel information carrying capacity. That is a fundamental property of qubit itself. Parallelism in GPU, what we do is a kind of an architecture method that we do to track certain kinds of problems. So
We inherently have this property.
yes, qubits have this inherent property of this parallelism. Bits don't. They are just two different things. We kind of take them together and then superimpose them and say that, hey, from now on you guys are working as parallel things. But qubits are inherently parallel. Shall we move on, or is there something else? Okay, cool. So now comes the interesting thing. Now that we know a bit about what these qubits and these things are we actually restricted to qubits? Like, classically it makes sense. There's something, there's nothing. Qubits, okay, come on, like, you were just baby steps, right? You just make the analog of it. So for 2-bit system, you are constructing some qubits. But are we restricted to qubits? So that's where my catchphrase comes in. Why to flip a coin when you can roll a die? So Einstein was actually wrong in the way God actually plays with dice, and we are going to play with it soon. So this is where I introduce you the concept of qudits. I think this is something that a lot of you would have not heard about. Qubits is a very famous, it's a buzzword, but qudits is something that is coming up very recently. Like, people knew about it, of course, but not until very recent, like dating 2020s, 2025. There, if you search qudits, you will find papers around the range of 2024, 2025, 2023. So it's very recent work. Yeah, so again, for the people who have had linear algebra course, why? Like, I can just go ahead and define a basis like this, right? What's the problem with that? Or I can do it for 4, or I can do it for 5, I can do it for any arbitrary D level, right? We can do that. So mathematically we are allowed to do this. Quantum mechanics never stops us to like create this very large column vectors, right? So in principle we have access to a whole new world. So that is where we are standing today. All these years we were able to catch up with what quantum theory has predicted. Now that we are actually catching up a little, like we are still not catching up. Like, to achieve the quantum supremacy you need some millions of qubits, but the state of art just has control over say 100, 200 qubits. So there's a long way to go, but still we are catching up. But as soon as we catch up, nature comes in and says that, okay, bro, there's a lot to go. It opens up a whole new door. Now you are not even restricted to say just 3 levels or 4 levels. You have arbitrary levels. Okay, you can do analysis in arbitrary levels. So that is where the concept of qudits come in. So there's this 3-level system, that is what we call qudits. Then there's this 4-level system that we call qquats, and so on and so forth. These are very recent concepts. So again, it's a generalization of qubits, these being D-level systems. Example, qudit. And again, the analogy being that if now I have a 3-phase die and I throw it towards you, okay, instead of that coin, you remember you had head or tail. Now say head, tail and a body, or 1, 2, 3, whatever. I throw it towards you. You don't know what that is unless you catch it. It's in a superposition of all of these 3 states going towards you. or a 4-phase die, or a 6-phase, or a 7-phase, or I don't know. Sky's the limit. So that's where qudits come in. And again, the concepts are almost the same. For example, qudits, there are 3-level systems now. So a ket 0, a ket 1, and a ket 2, right? What would be the size of the quantum operators that work on these qudits? 3 cross 3, of course. For if you were working with two qudits, then the size would be, and for 3 qudits, get it right. And again, they can exist in a superposition of 0, 1, and 2. So on the very first step, you can realize that there's a heavier, there's a dense quantum information carrying capacity, right? It's not just 2 quantum states anymore, it's 3 quantum states, and it's a 3-phase die. Why qudits? The first is higher information carrying capacity, no doubt about it. You have higher access, the vector space is larger, so yeah, it's higher. More efficient quantum error correction code. So this is something, let's talk about it. So in classical computation, noise is an inherent part of the environment. You cannot just escape the interaction of information with noise, right? There will be some noise to it. So there's this fundamental correction codes that we need to basically, revert the effects that noise has imposed into the problem. So for say a quantum information processing task, you need a lot of qubits to even get that error correction done. Like for example, the Shor's algorithm thing, or the algorithms that has real world application. You need, say for example, 1,000 qubits to actually do the computation thing. For example, the circuit, you remember, instead of 2, you need say 1,000 of qubits to do a circuit, to do the information processing. Or say for example, the protein folding circuit that you saw a few slides back, you could see there were a lot of points, like say 7, 10, some number of qubits. Whatever, say 1,000 number of qubits you are using. But it's not enough. You might end up interacting with the environment and then lose the information about the state. So then you need even another 1,000 number of qubits to revert that. So that is where the error correction thing comes in. So this quantum error correction is a huge branch to study, how we can actually do this error correction stuff. But with the introduction of qudits, we might not need those 1,000 qubits to even do the error correction, right? We have larger information carrying capacity. So perhaps 100 number of qudits should do the job, or perhaps a 500 number of qudits should do the job, right? Again, these are open questions. These are open questions. Like, people are working on this. People are finding efficient algorithms. People are finding the analogs of those qubits algorithm. And people are working more on them. People are trying to figure it out. Can we get some kind of advantage using those qudits? We have found a lot. We have found a few, but yeah, it's a long way to go. There's a potential for even stronger algorithms. Just like the Shor's algorithm, you can have some different algorithm which can actually do work better, because of course you have a greater ground to play with, right? And this richer entanglement structures. So with the 2 qubits, this entanglement thing that is making you crazy, people going crazy all around it. For 3 qubits is even crazier, and for say n number of qudits and stuff, you can only imagine what kind of entanglement structure we can only get. So that is why qudits are being explored these days. How qudits are encoded? Pretty much the same idea. You remember the harmonic oscillator? If I just add another state to it, now you have qubit. Add another state to it, now you have q quad. So you just realize doing this is an experimental task. You need a quantum information guy to actually figure out how this quantum information would do, how this quantum information task would be performed. But then doing this would be an experimental or an engineering task. Like, can you probe them? Can you probe them? Now we can probe them. So yeah, we can construct a qubit. We can construct a qubit. You can construct it right here in the labs. You can do that using the photon lab, using the photons and stuff. So we can actually make these qubits, and we can actually make these qubits. We can actually make these q quads. Okay, we can do this. So yeah, that is why qudits are getting more attention, because we can actually probe them now. So these are some examples of qubits. So now instead of just using the horizontal vertical polarization, you can use the orbital angular momentum thing. I think most of you would, like if you have had some kind of quantum mechanics course, you would know that the orbital angular momentum are quantized, something called L square operator and LZ operator, that gets you some kind of quantized, something of this. This is a quantum number, ms. Like if you don't know, it's fine, but basically think of it as now we have some quantized states. So basically say -1, 0 and 1. These are the only 3 states that are accessible. So now basically you can access them and you can use it as qubits or qubits or whatever. So these are certain ways how qubits are encoded. You can like Google them, such a video in YouTube, and give them some idea about it. The challenges are very like qubits are very difficult to handle. It's very difficult to handle for the fact that it's so large that you can actually lose track of it. You cannot like maintain entanglement structure for long. You cannot maintain it. It's not easy. Given with qubits, it's even harder. Like the entanglement structures are even more feeble in the sense that you can like lose it in snap. Okay, so it's very difficult to realize them experimentally, and it's very difficult to actually control them. You need very, very, very precise measurement techniques to control them. And it's like hard is just a word to like, it's almost impossible to simulate them classically. It's very difficult. It's very difficult. Simulating qubits is very difficult because I'll tell you even I'll tell you another part to it just after the next slide. So where do we stand today? People are working on these areas, that being qubits in trapped ion systems, superconductors. Like just we realize qubits, can we realize it in qubits? Photonic qubits, same thing. Can we realize qubits using photons? Exploring qubit error correction course. Can we do the error correction better in a better way using these qubits? Hybrid qubit system. Just like as I said a few minutes back, we are not vouching for all quantum computers. Like we are vouching for a hybrid quantum classical computer system. Similarly, we are not vouching for an all qubit. Like bigger is not always better. Like for example, if you look into certain mathematics, you can see that 2 is sufficient. After that, it's redundant. Okay, there are a lot of problems. If you do the maths, you'll see that 2 is the largest number you need. So for certain cases, qubits is enough. That's it. After that, it's just redundancy. Okay, so there's a smaller class of problem where qubits would come handy. So again, we need a hybrid qubit system. So we are looking at a utopian world where we have a great synchronization between a classical computer and a quantum computer, and a quantum computer basically works with qubits and qudits at parallel, and this entire thing is like it's Star Trek stuff. So yeah, like that is what we are actually trying to do, and it's like 100 of years ago. Yeah.
If we are taking higher orders, is there any reduction in scale or what's the disadvantage that we get?
Pardon?
Instead of taking 2, when we are taking higher numbers, and we find out that 2 is enough, what's the problem if we take more than 2?
I mean, again, like if you are getting redundant states, then I mean handling qubits are not a matter of joke, right? Like you can handle 2 qubits easily, but then to handle 2 qubits, you need higher job, so higher work for that. So yeah, you just end up losing more energy to like even maintain them. So it's not use. It's of no use. All right. So that is what the hybrid qubit systems are. And then finally this algorithm thing. This is where I work in. So a bit about my work. I am working in this domain of qubits interacting with open dynamics. So basically it's a many body qubit system interacting with open dynamics. So that's the nearest we can get to a realistic quantum state, right? So a realistic quantum state would be something that is say sitting in this room, say interacting with this environment, and there are say n number of them. That's the most realistic system you can ever think of. So I am working with n number of qubits interacting with the system. So it's an open n qubit system in a way. So there we explore how this noises actually interfere them, and I'll tell you it's very difficult to compute them. Like I have crashed the DCF computer so many times that you can't even think about it. Okay, so I just end up making it hang and then like shut it down and then open it. So it's very difficult to simulate them. Very difficult. Like even a meager number of 10, 20, you just let it run for like 5-6 hours. And for even difficult structures, for even my friends who are working in this, for difficult structures, for reinforcement learning models used to track these things, they let it run for 2-3 days, then they get a result. So it's that difficult to simulate it. So yeah, it's not just harder, it's almost impractical to simulate these quantum systems on a classical computer. So yeah, you need these qubits for that. So if we have greater control over qubits, we can actually do these algorithms that can actually give us better results. For example, the protein folding problem that you will see, the variational quantum eigensolver, it's a very famous algorithm that works on this principle. So yeah, there's room for even more algorithms, and with that I'd like to just end saying that the quantum revolution is at our doors, and it's just here, and there's a problem for everyone, no matter if you are a pure mathematician or you are a hardcore engineer. There's a problem for everyone. Like there's problem in complexity things as well, and there's problem in real experimental problems. So yeah, try your luck, get yourself into one of the problems, and I'm pretty sure that you will have a lot of fun solving them. So yeah, enjoy the Qiskit Fall Fest, and yeah.
You said that simulating qubits in classical computers is nearly impossible.
Yeah.
So how do we go forward to be able to simulate that?
Okay, so it's not impossible in the sense like we can do it, but it's very difficult to do. Like for example, what I do is for my system I assume some kind of symmetry. For example, we can think of say n number of qubits or n number of qubits. They're interacting to a source term in an independent way. So there's some kind of symmetry in the problem. I invoke that symmetry to compute at a smaller, like truncate the size to a smaller scale. So sometimes you, like Taylor expansion, what Taylor expansion does. Sometimes you don't need all the higher order terms. You just need some terms, and then you can truncate it, and that's it. You can get an idea of the function, right? Similarly, to simulate some kind of systems, you don't need every detail of the system. Perhaps a smaller subsystem would give you the information. So these are some of the ideas, the so-called truncation ideas that we use to simulate them classically. But again, if we have access over qubits, then we can actually use it using the qubits. Then it's just like it's very easy to simulate. Yeah.
Like, what does Qiskit allow? Like, the module, what does it allow?
The Qiskit module itself. So Qiskit, what it does is it has a way for you to construct different types of circuits, like all those Hadamard gates and the C0s and swap gate, whatever you saw, you can actually construct them. Qiskit has a very extensive module in the sense that you can apply it for chemistry problems, you can apply it for economics problem, and you can actually take up the ideas from this quantum algorithms, the speed up that they basically promise, and then apply them there. Like for example, a very simple idea would be in quantum mechanics you have a Hamiltonian, you find the lowest energy to that. Okay, so that's a very simple idea in quantum mechanics. So this is something like this: some h psi gives you some e psi. It's an operator. You have some Hamiltonian, you get the state, and then you get the lowest energy state. For classical case, you can think, like for example, you can think this Hamiltonian to be some kind of cost function. Like say for example, you want to minimize say some kind of parameter in your problem, and then find its the smallest energy. As soon as you get the smallest energy, you are kind of optimizing it. So these are the ideas that are taken up from quantum mechanics but are applied in real world, and that's exactly what variational quantum eigensolver is. So it solves you this eigen equation, gives you the optimized value using the ideas of quantum mechanics. So that's all about it. Okay.
If there are no questions, we can.
All right. Thank you, everyone. Enjoy the Fall Fest.
Any questions about the event itself also you can ask now before we wrap this up. Not just about the talk, about the scheduling or any of the problems or anything. You can ask now before we.
Yeah, that was a great Boltzmann by Sayam. Thank you so much. You introduced us to Qubits and then went to Qubits and gave a reality check on how quantum communication and quantum computation is. And thank you for that. I hope you guys enjoyed the Boltzmann. And yes, sure. If you have any doubts about the fest itself, you can ask it now. And we'll be sending the relevant links and resources in the group soon. I think.
Did you join the question?
What would we learn in the fest? Like what all would we learn?
So first, the fest would contain an introduction to quantum computation, Qiskit, and we'll have a tutorial on that, a basic tutorial. Then we will learn about protein folding and QKD, which are the applications, two of several applications of Qiskit. And we'll see how we solve the problems using tutorials. Again, we'll have a learning session which is about 2 hours to 3 hours of learning session. Hands-on, you have to get your laptops to one of the CRCs. We'll have a hands-on session followed by a tutorial. We'll be launching it. Then after those 3 tutorials, we'll have a hackathon on November 1, a 24-hour hackathon. Where the hackathon will be based on the topics that were discussed in the tutorials. Then after the hackathon, we will have the closing ceremony with a keynote lecture on the future of quantum and history and future of quantum. Then we'll give up the prizes.
I think it's even before the event is essentially a month from now. Even before that, we'll share a lot of resources to help you get prepared before you actually start implementing any of the problems. So you'll have at least a few weeks where you can practice before entering the actual event also. So any other questions?
Also in the groups, the WhatsApp groups, we have shared the volunteers Google form. So if you guys want to volunteer, the QQ, we call it the Q crew. So if you guys want to sign up, and like you mostly will be involved in correcting the tutorials and what else, like
Logistical.
minimal logistical work, but mostly it will be correcting the tutorials. So before that, in these 2 weeks, 3 weeks I guess, around 3 weeks, you will be learning. You will be learning Qiskit, and so that you will be able to correct the tutorials during the Fall Fest. So if you are interested, you are advised to fill out the volunteers form by tonight 8 p.m. That's the deadline. So we'll be sending the form again in the respective groups. So yeah, that's about it. And anything else that you guys want to know? Also, we will be releasing the registration form, basically the website, tomorrow. We'll let you know the time soon. And the registrations that we get from the time that we mentioned tomorrow would be considered. So we'll add a column to upload the UPI payment screenshot in the website. So we are yet to do that. So the registrations that we get after the specified time only will be considered. So refrain from registering now. We'll let you know exactly what time after which you can register. Okay? Anything else? Yeah. I hope you guys enjoyed, and if you have any more queries, you can contact any of the admins in the group, that the QC Society and Astrophiles. And yeah, this fest actually marks, not fest, this year actually marks the 100 years of quantum, like the start of quantum. So that's why this fest is really more special to us. So I hope you